Today, we're going to be talking about network security. But what does that mean when almost any device you use will be connected to the internet, and many attacks in any context will be launched from a network-connected device? Well, one answer is that it's all about keeping the baddies out. If you're running the local network of a company, or even a home network, with many devices connected locally and to the internet, then you want to protect your internal network secrets from leaking out. And you may also want to prevent any of your internal devices from being used to launch attacks. So, conceptually, we have an internal network with many local trusted devices, an external untrusted network of devices, and some sort of filter in the middle. This is called perimeterisation. You try to isolate off your local part of the network to limit the potential for attack, with both blocking and logging potentially playing a role in keeping the network safe. But is that really the right place for protection? What is a perimeter of a typical business anyway? Isn't the idea that we trust all of the devices in our local network, potentially with malware-ridden bring-your-own-devices, a little bit naive? And what are the limits of the perimeter? When people want to be able to connect in from home, possibly using VPN or virtual private network technology, to pretend they are part of the local network. The alternative, which is increasingly becoming popular, is deperimeterisation. Rather than placing the trust at the edge of an internal network, the idea of techniques such as Google's BeyondCorp is an architecture mostly without firewalls, a zero-trust security model where each service on each device has its own tightly defined access controls and authorization primitives. That's neat when you can do it, as it avoids the increasingly fallible assertion that everything inside a local network is trusted. But sometimes a traditional perimeter with protection at the interface is inevitable. If you need to support an old protocol such as CAN bus in a car, then the internal network can't be protected, and so protection has to sit at the edge. The same is true if your internal network is highly performance sensitive, where going to town on cryptography might be just too expensive. And then there are some attacks such as denial of service, where local devices just might not be trustworthy enough to give the privilege of defense. The intranet itself needs to do the protection in a firewall. Okay, so first, what kind of attacks are we interested in when we talk specifically about network security? We should start by considering attacks on the network itself, rather than any that might be facilitated by the existence of a network. Well, the internet was primarily designed around resilience and scalability, resistance to failure with non-malicious users, which is more about links being broken and restored very neatly rather than about security. Because the internet is a distributed system with many independent actors, it's difficult to change the protocols involved, which tend to fossilize, and therefore you have to build around them if you want to make them even vaguely secure. BGP, or Border Gateway Protocol, is used in the internet, in the wider internet, between autonomous systems, i.e. between internet service providers, telcos, large organizations, to route traffic between them. It's designed to be able to deal with failure, so networks being disconnected and reconnected, but there's no intrinsic security. It's trivial to advertise a false route on this. There's no verification whatsoever, and we've seen lots of examples of this going wrong. In 2008, YouTube was taken down over the entire internet because Pakistan tried to censor it locally by advertising false routes over BGP, and the false routes escaped out, meaning everybody's traffic received an incorrect route through the network by BGP giving them completely the wrong path through the network. In 2010, China Telecom took down about 15% of the internet for 18 minutes by advertising 100,000 invalid routes. And there are various instances in the past of intelligence agencies using BGP to not just advertise a false route, but advertise a route with some false nodes in the middle. So rather than going direct, you go via this falsely advertised route, which means you'll still get there, but all of the packets will be able to be collected. You've got a man-in-the-middle attack. There are lots of other attacks, like cryptocurrencies being stolen by false BGP routes, and so what we're saying here is that kind of the entire basis of the internet is utterly unprotected. Well, that is true, but there are various things you can do about this in practice, even though many of them are quite indirect. One of the easiest to do, which is really quite indirect, is accept a limited number of routes from each peer in the BGP protocol. So each system in this distributed system can only advertise a small number of routes, so they can't poison the entire internet. If you want to start poisoning traffic wholesale, then you'll need to be able to take control of lots of these different autonomous systems, which is more difficult. There are what we call Internet routing registries, which are a separate data structure storage mechanism from BGP, the protocol itself, that keeps a log of where things are and where they should be. You can see from that if there are false routes that aren't advertised, but it's filled with lots of incorrect data anyway. There's lots of stuff in there that's known to be wrong, but nevertheless not malicious. Then we've got companies like Cloudflare who offer what are called BGP collectors, which will periodically collect routes that are being advertised on the wider internet and just compare them to see if they're wrong. So there is a logging functionality. We can tell when things have gone wrong in the internet, and that's at least some reassurance. The latest technique in the area is Resource Public Key Infrastructure, or RPKI. You add on this secondary data structure that is protected using public key cryptography that signs all of the routes. So what you get from this is autonomous system X announces IP address range Y, and it's signed so we know it really was from the autonomous system X. But there are several things here that don't really work, at least not optimally. Does adding public keys really make it more robust? No, it just adds another source of failure, in that you then have the public key infrastructure of certificate authorities in the way, which certainly makes the system less resilient, even if it might make it more secure. And we'll talk a little bit more about how much you should trust the public key infrastructure a little bit later on. Just because an autonomous system has announced that they're offering a route, and you believe them because of the public key infrastructure, doesn't mean that it is a correct or direct route to them. So really this is more about about protecting against accidental breakages. It means that you've got an extra step in the way for you to start advertising false routes, rather than necessarily that much of a security benefit. The other issue is that for something like RPKI and many other things in the internet, because the internet is this really open distributed system, it's really very difficult to change things. So there haven't been that many adopters of RPKI, and it's not extremely widely used, though that may change soon. Cloudflare is a big proponent of it, and so we'll see how widespread it gets deployed. Another reason that we perhaps shouldn't be so worried is that if you're using HTTPS for your connection, yes, the BGP protocol might direct you to the wrong place, but assuming that all of the public key infrastructure is working correctly, the other end won't be able to respond and pretend to be the correct destination. Because you've got cryptography in your HTTPS connection, though you can still get man-in-the-middle attacks and you can still get denial of service where you'll get the wrong route, you just won't think that it's the correct endpoint that you're communicating with in that scenario. So speaking of denial of service attacks are possibly the most prominent attack on networks these days, especially distributed denial of service attacks, or DDoS. The basic idea is that you try to take out the service of your enemy, perhaps a rival country, company, or rival video game player, either through overwhelming their resources or through getting them blacklisted from a service. For resource overwhelming, the basic idea is that you flood them with lots of network packets. But to do that, you need to be able to generate all of that traffic in the first place, right? Well, not necessarily. A traditional way of bumping up your ability to attack is via amplifier attacks. There, you convince other legitimate actors to do your bidding for you by making them generate bigger messages than those you had to use to communicate with them in the first place. So, for example, let's take a look at the protocol TCP used to set up persistent, reliable connections over the internet, including for things like HTTP. In this example here, we've got a TCP packet, i.e. the packet used for things like HTTP and HTTPS, and what you have is a SYN and an ACK that sets up the communication. Many attacks have been done in the past, such as SYN flooding, where because the protocol is stateful, a malicious Alice can trick an innocent Bob into holding lots of state about connections that Alice does nothing with. So you have to modify the protocol to include the state in the reply via SYN cookies. But today, SYN reflection is more of an issue as it's hard to fix. If Alice sends one SYN packet to Bob pretending to be Charlie, Bob will send up to 5 ACK packets in response to set up the connection if it fails to get a response. Charlie obviously won't respond with an ACK in return, as it was really Alice who set up the connection. Still, Charlie gets hit with 5 times the traffic Alice could otherwise generate, and so Alice can overwhelm Charlie with only a fifth of the bandwidth necessary to do so. Many other protocols on the internet have similar amplification potential, including DNS and NTP. Famous ones in the past included smurfing via ICMP, the Internet Control Messaging Protocol. Still, a fix to make these amplification targets harder is implemented in most operating systems nowadays. Windows stops you from sending out packets from a faked IP address, so unless you hack into the operating system itself to change that, you're forced to generate such fake traffic from your own machines, or at least from a data center. Why does that matter? Typically, an attacker won't want to use their own machines for an attack. Rather, they'll be issuing distributed denial of service attacks, or DDoS, by commanding a botnet, or a series of machines they've infected with malware to do the attack for them. So, since you, the attacker, will want to issue your attacks from commodity machines, which are a challenge to issue faked IP addresses from, this makes amplification less common nowadays as a method of improving the effectiveness of DOS attacks. Rather, the attacker will just use more machines to generate messages from. What is the point in doing denial of service attacks anyway? In the UK, they're very, very illegal. Under the Computer Misuse Act, a DDoS can get you up to 10 years imprisonment. And yet, if you go online, you'll find it very easy to find a booter for a few dollars, who will use then botnets to attack your target. Typically, these are marketed towards teenagers attacking each other's TeamSpeak servers to stop opponents in online games from being able to communicate properly. I mentioned already in the first lecture that actually the easiest way to shut these down isn't technical, it's legal. The FBI periodically raids operators of these, causing them to close down, sending up the market price for DDoS for at least a bit. As well as conventional malware on conventional machines, a huge source of devices for DDoS botnets is actually Internet of Things devices such as CCTV cameras. The most famous of which is the Mirai Botnet, which took down Twitter for several hours in 2016 by attacking DY and DNS, preventing the successful conversion of domain names to IP addresses. Several copycats have appeared using the same strategy since. Why? Because IoT devices are a perfect target. Typically, users of internet-enabled CCTV cameras will want to be able to view them remotely, and so the camera will have to be able to punch a hole straight through the firewall for valid use using something like UPnP or Universal Plug and Play, so it will have very few protections placed on it. The device won't be running something like Windows, so it won't get security updates, and it won't get patched once flaws are found. And they're likely to have default passwords, so once some malware gets into a computer on the internal network, The malware can add itself to the list of authorized users of the IoT device and stay there even if an infected computer has the malware removed from it. And why aren't purchasers of IoT devices more worried about this? Well, why would they be? It's not the owner of the attack that's getting attacked by the DDoS partially launched from it. This is a classic example of misaligned incentives, in particular a negative externality. Alice's insecurity is paid for by Bob, and so Alice's incentives are misaligned in fixing it, even in the unlikely event that they know their camera is infected by malware and being used for a DDoS attack. And that brings us to malware more generally. It's a fairly cover-all term that we use when talking about malicious software that comes under many different names with overlapping meaning and usage, but we can try to be more specific here. First, we have viruses which attach to executables and change their code in order to run the attacker's code instead. The detection challenge for an antivirus is that the code may encrypt itself or otherwise rearrange or obfuscate to avoid matching known patterns. Then we've got worms. These spread themselves over the internet via broadcast mediums such as email or network protocols more generally, and each infected machine is also used to infect others. These are less popular than you would think, at least for commercial malware writers, because anything that spreads too quickly gets detected and the vulnerability patched too quickly. A noted exception to that being Mirai, because it attacks devices that don't get patched. Next, Trojans. These are programs more generally that do something malicious when run by an unsuspecting user. Unlike a virus, this malicious behavior isn't necessarily injected into an otherwise legitimate program, but the program may appear to have other legitimate functionality. A remote access Trojan, or RAT, enables a remote actor to access the device it runs on. Rootkits. These bury themselves in a system, claiming root privileges for a third party to control it. Potentially unwanted software, or POS, is more ambiguous. Think about things like third-party browser toolbars. They're software that is often installed deceptively and does things the user doesn't want or understand, and yet may be installed by pseudo-legitimate actors or other software that the user does want in the name of ad revenue. Fitting into a similar category are unwanted software such as stalkerware. It may not always have the hallmarks of a virus or Trojan, and it may have valid desired usage, such as by court order or as a condition of bail. But it can also be installed covertly or otherwise by an abusive partner or by fraudsters looking for remote control. Even antivirus software itself may sometimes fit into the category of PUS. Often these products, even real ones, can be installed as part of free trials that then take root and can be very difficult to remove without paying money, or they may introduce insecurities themselves. Should we be surprised? Not really. Antivirus software is a classic example of a market for lemons. Who knows which antivirus software is any good? So the poor quality ones often end up dominating, and that's why modern operating system security is as much about clever use of access controls than about antivirus software, even if antivirus software is an important component of a Windows setup, and Windows comes with its own suitable tool because there's a market failure otherwise. If you're wanting to analyze malware, then you've got a couple of different options of the tools that you would use. One is GHIDRA, G-H-I-D-R-A, which is the one that's shown on screen. This is a tool that's actually from the NSA. It was revealed in a leak and eventually made open source so anyone can use it. And it means that you can disassemble binaries, especially malware. Another alternative includes IDA Pro, and if you're a big company that's a prize target, you may need expertise on binary analysis in-house because you may get unique attacks on your systems that are very targeted. We talked in the first lecture about the idea that nation states will use 0 days only on opponents that they don't think will be able to reverse engineer them unless it's absolutely necessary for them to, because they're so expensive. So having this capability may be a good protection for you from 0 days. But why do all of these exist? Some might have been designed by hobbyists whose creations got out of hand. That's certainly where some of the earlier examples came from. But like everything else, malware has become commercialized, and so most malware writers have more firm incentives. This can be ransom encryption. Your files will be lost forever unless you send me some Bitcoin. It might be more direct and be designed to access your bank account or exfiltrate your company's data. It might even be for surveillance by all kind of actors, from governments to jealous partners. It might be just to mine cryptocurrency from your electricity rather than the attackers, or to create a botnet for DDoS attacks like the Mirai example we talked about earlier. If you look in the Google Secure and Reliable Systems book that I've mentioned previously, the categories they put it into are fun, fame, activism, financial gain, cohesion, manipulation, espionage, and destruction. And these sort of all often get muddled together. And nation-state attackers' software can sometimes be used for all of these, especially since it can often get into the wrong hands, like the shadow broker attack on the NSA that we talked about in the first lecture, which leaked all of their tools. And also there was a case in China where some nation-state attacker code ended up being used to steal video game currency via something called Winty. And that brings us back to the perimeter again. If you've got a network of any reasonable size, you're bound to have infected machines within the network. Is it really okay that some malware can sit on your network harvesting any passwords traveling in plain text over the network, or are you going to have to use SSH or Kerberos over the top to encrypt your local communication, handle access control? In the olden days, you might have been able to control and monitor all software run on devices within your perimeter. But what is the perimeter now with VPNs and bring your own device? If you really want to gain full access to a local network, the best way to do it is to spearfish a sysadmin, i.e. send them a very targeted social engineering attack. The targeted part is the spear in phishing. You monitor traffic leaving the domain to identify sysadmins, then send them a convincing lure, such as a spoofed website or even a real website with a man-in-the-middle attack, to steal credentials or force them into downloading a rootkit. Any system you design will need to be resilient in the face of such attacks. It's not sufficient to just blame and train. If you look at the Google Secure and Reliable Systems book, the advice they give you is, if you can't completely stop criminal adversaries' attacks, because there are some very capable adversaries out there if you're an interesting target, then what you want to do is make the attacks really expensive, with things like captures in the way, so they'll go after easier targets and leave you alone. Also in the Google SRS book is this idea of insider risk, which is especially relevant in the network sense, because you might have insiders in your network, whether malware or malicious employees. So you need to design any system, especially a network-connected system, to handle that insider threat. Much of this is about logging, so you have a record of anything happening inside your system. What we have here are least privilege, granting the fewest privileges necessary to perform job duties, both in terms of scope and duration of access, and that applies to software as much as it does to users. Zero trust, designing automated or proxy mechanisms for managing systems so insiders don't have broad access that allows them to cause harm. You have something in the way of their authorization so that they can only do a limited set of operations. Multi-party authorization, using technical controls to require more than one person to authorize sensitive actions. As well as stopping against malware and infected actors, it can also help defend against blackmail attacks so that you can't just threaten the family of one person and get your way in. Business justifications, requiring employees to formally document their reason for accessing sensitive data or systems. Auditing and detection, reviewing all access logs and justifications to make sure they're appropriate. And recoverability, the ability to recover systems after disruptive action, like a disgruntled employee deleting critical files or systems. Or even, as we discussed in the first lecture, a zero-day attack that you've realized you've been vulnerable to, where you might have to very rapidly rotate all of your keys and have them built afresh, so that you want to have a system that can handle that sort of recoverability and rapid recoverability that won't itself break when you need it to work. And there's this term called chaos engineering, where in many systems you'll add random failures into the system deliberately just to make sure that you can deal with actual issues when they occur in actual failures. So you'll have things failing all the time on purpose. So what does a competent network defense look like? Well, network security in general is effectively a bodge of many different solutions, and so these days there will be many different components, some at the edge and some on device, and not all of them technical. Governance and management, such as bring your own device policies, are also important. As well as threats from outside, you may be worried about threats from within, such as data leakage prevention systems to identify staff who are exfiltrating company data or code. Still, while the tools are complex and varied, they mostly fit into two different categories: filtering and logging. On the filtering side, most networks will have a firewall sat at the connection to the outside world, which will filter out bad-looking packets. Some of these rules are simple, for example around IP address spoofing. The firewall can block packets from leaving the intranet of a forged source to stop it from being used for attacks such as amplifiers, and can block packets arriving from outside the network with an address forged to be inside it. It can also block IPs from a known list of bad ones, which need updating and may struggle if the bad IPs change very rapidly. By default, firewalls will block all ports except those used for email and HTTP requests and only open others as needed. Still, sometimes packet filtering isn't enough. You need to be able to see the full stream of traffic to work out what should be blocked. For example, if the packet is fragmented in such a way that the initial fragment passes the firewall's inspection, but is then overwritten by a subsequent fragment, replacing the source address with one that violates your security policy. There you need circuit gateways, filters that can reassemble packets into entire TCP sessions. That moves the analysis up the IP stack and can also provide other features such as VPN support to encrypt packets between different private intranets. If you want to actually look at the content being communicated, such as blocking bad images or code, then you'll need some protection at the application layer, often on device rather than at the edge of the intranet. Email spam filters are one such example, or email filters that remove executable attachments. There you need to understand the content to block it. Filters that look at application level data can conflict with other aspects of security. If the contents of packets are encrypted, for example on HTTPS connections, then this usually won't be possible to filter at the application layer in a perimeterized firewall. This could become even more challenging if technologies such as DNS over HTTPS, which encrypt the traffic that converts domain names to IP addresses, get adopted, because then attacks such as hijacking of DNS services or DNS servers or visits to known bad addresses will be more difficult to spot. So security on one side can cause problems of resilience and lack of visibility on attack on another. So you need to be careful about whether it is worth losing this logging ability to add more security and signatures into systems. It may not be. So coming back to the deperimeterisation versus reperimeterisation angle, where should your protections be? Where will they be more simple to provide? After all, it's not just malice that you'll have to deal with, but error too. Where is simplicity needed? If you have a complex, diverse network, then placing your security in a small number of elements might make things easier. Whereas if you have lots of identical devices, then you'll be able to control their setup more precisely and move the filtering into each identical device. In the limit, splitting up your perimeter into multiple levels of trust ends up being deperimeterisation. Everything runs as a microservice with its own application-specific perimeter and firewall, with application layer firewalling. But there are a spectrum of alternatives here. If you want to split things up into, say, the example here, where we've got our web server on the outside with a firewall protecting it, and then we've got our intranet, which is digital devices that aren't necessarily trusted, but we don't want to be visible to the outside world, unlike the web server. And then you've got the classified intranet, inside which has all the things that you really care about security, where you lock them down extensively and don't allow anything more risky to happen inside them, because they're known quantities with known behavior and you can ban anything unusual. And you don't have anything that can do anything unusual within that classified intranet. You can do all this virtually. You don't need to have physically detached networks. You can implement it using a virtual LAN or VLAN with network access control lists to work out who's allowed to talk to who. How big should your network be? Do you need to have your accounting operations on the same network as your R&D lab? And even if you can, should you? If some parts can be controlled and others can't, then the best approach might be separate architectures with separate perimeterisation strategies. There's also incentives to think about. A sysadmin who looks after a departmental server used by 100 people they know, and who will personally have to clear up the mess caused by an intrusion or a configuration error, is much more motivated than someone who's merely one member of a large team looking after thousands of machines. So even in network security, there is the human factor to think about in terms of network management. The other danger with protections in the network is that if you block too much, will people have to circumvent it in order to do their jobs effectively? If you lock down your corporate email too heavily, people will move to their own infrastructure instead. There's a real compliance budget issue in much of networking security. Your firewall might be locked down, but if you're trying to get something just slightly out of the ordinary working, like an online game instead of an email or HTTP request, then you might end up having to punch a hole through that security using UPnP, Universal Plug and Play, or the game might be written to mask its traffic as standard HTTP to get through that firewall anyway. Or worse, your user might just switch off all protections altogether. Fundamentally, you're going to hit up against the receiver operating characteristic curve, or ROC curve. Do you overblock to be extra safe and cause some users to turn off the system and warnings to be lost in the noise, or do you underblock and let the bad guys through? Where overblocking is a false positive rate over here and underblocking is a true positive rate down here. Well, not all aspects of network security are about filtering / blocking. The other angle here is monitoring and logging in the forms of intrusion detection systems, or IDS. These sit at a different point in the ROC curve. You don't block behavior, you instead just send it for further analysis, so you can tolerate a slightly higher false positive rate if it means fewer things fall through the cracks. This falls into two categories: misuse detection and anomaly detection. Misuse detection is perhaps the most straightforward in that it involves a more precise model of the attacker and how they operate. In this category, we have simple things such as threshold alarms or signature detection, looking for known sequences of indicators of bad behavior, perhaps even using classifiers trained on a large number of signals. Why would you want to sound an alarm or log this rather than outright blocking the behavior like a firewall would? Well as the ROC curve issue, where false positives overwhelm your true positives by noise, the other problem is denial of service attacks. If your attacker can break your system by issuing sufficient requests to trigger the threshold, then you're in trouble. Anomaly detection is the harder job of trying to find unusual behavior without such a concrete model, in the hope of finding new types of attack being performed on your system. Again, you can use classifiers to do this, but training machine learning models to spot unknown behavior is far more challenging than spotting known behavior. And so false positive rates become a real danger, especially if it causes real issues to be lost in a sea of false alarms. If the signal is way below the noise, i.e. the real attacks are outweighed in quantity by a vast amount by the false alarms because the attack's rare, the guards will just stop paying attention, and so genuine alarms get missed. Often it may be better to just measure simple properties such as significant changes in user request rates. The lines between the two can be blurred. An example from the world of accounting is Benford's law. If you're trying to fiddle your accounts, you might expect that picking numbers uniformly at random would look fairly realistic. So a number beginning with 9 is just as common as one beginning with 1. But as it turns out, when numbers are randomly drawn from natural sources of information and span at least an order of magnitude, about 30% start with 1. So thinking up numbers or even using a random number generator is likely to follow a very unnatural distribution, which often gets crooked accountants caught. If you have systems that are likely to be attacked in novel ways, then your best bet may be in honeypots. Rather than trying to model bad actor behavior or discover unusual behavior, you're trying to catch them in the act. If you're a hospital, you can have dummy records with celebrity names in to catch leaky staff. If you're running network systems, you can connect an emulation of a potentially faulty device into a virtual machine to measure who tries to access it. There's this book here called The Cuckoo's Egg, aka Stalking the Wily Hacker, which is the academic paper version, which details such a process from one of the earlier days of the internet. It stemmed from the discovery of a simple accounting error at Lawrence Berkeley Laboratory, the national laboratory in the US, that turned out to be someone in Europe trying to steal state secrets for the KGB. And there's sort of a fun, adventurous trek through that whole process in this book. So, taking a step back, what are the real challenges in intrusion detection? Fundamentally, the internet is a very noisy place. A lot of bugs can appear innocently of any malicious intent. A packet supposedly from your own intranet arriving from the other side of a firewall might be an attacker trying to trick some devices on the inside, or it might be a packet that's accidentally escaped and come all the way back round again. As we've discussed already, if the true positive rate is low, then you'll struggle to distinguish signal from noise. An alarm that goes off incorrectly just puts the guard to sleep, stopping them from catching the real attacks. Though machine learning classifiers can sometimes be the solution, we should always be wary of their limitations. If we're looking for alarms on unusual behavior, then we'll struggle since neural networks are poor at extrapolating outside of their training set. Part of the issue is that often there are no obviously incorrect states left by attacks on network infrastructure. If someone's stolen money from a bank account, then there'll be an auditing trail, but if someone's stolen some data, who's to know? As a defender, you'll always be playing catch up with the attacker. The attacks change as often as the software, and so you'll need an ever-growing set of signatures and even strategies that can handle the kinds of code obfuscation we see in virus writing to get around signature detection. Given companies often install IDS systems for compliance rather than real defense, the quality of updates to intrusion detection systems often leaves something to be desired too. They may not be any good. As more of the internet becomes encrypted, it gets harder and harder to have perimeter defenses. Most traffic is already HTTPS rather than HTTP, and if DNS starts going over HTTPS too, detection will get worse. You won't know when devices are communicating home because you won't be able to spot it as easily. So you won't be able to spot people who have installed bugs on your system quite as well. There are global versus local detection issues that only get worse with deperimeterisation. What if an attacker sends out millions of packets, but only 2 of those go to you personally each day? You aren't going to spot them using some sort of alarm system that's based on a threshold. There are lots of cases where you need secrecy or authentication in networks, and the answer really is often cryptography. Let's have a look now at a few places where that manifests and some places where it doesn't. Wi-Fi is one such example. Early on, the standard of encryption was very patchy. The WEP standard was hopelessly weak due to both the crypto wars, meaning the key was really short, and a series of implementation failures. But WPA2 is now supported by most devices, meaning WEP can finally be disabled and is disabled by default on most routers, and is stronger and uses AES as its cryptography standard, which we know its strengths and weaknesses of quite well. One question we might ask is a Wi-Fi network a perimeter? Is every device on there trusted? Often the password is mainly to stop unwanted use of quota or bandwidth by strangers, and many people and businesses have open connections. Do you have to trust everyone else that wanders into a coffee shop? A big issue has been default router passwords. If someone gets onto your network and the router's password is admin, then you can end up with obvious issues given the uncertainty of trust of many devices on most networks. Why is that trust so uncertain even if you have your network locked down? Well, what happens to old devices using flawed Wi-Fi chips like Android phones that only get patched for 2 or 3 years? What about IoT devices or your child's Wi-Fi enabled doll with a microphone attached to it? You get similar issues around Bluetooth enabled devices, and there have been very serious patch cycle issues around various network connecting devices, Mirai again being an obvious example. VPNs, or virtual private networks, are another. These do encryption and/or authentication over IP packets to funnel them between different trusted perimeters over the untrusted internet, using a protocol called IPsec. There have been leaks that suggest the default settings for key exchange, a 1024-bit Diffie-Hellman protocol, can be broken by the NSA, perhaps due to weak random number generation inserted by backdoor in its design. So it probably isn't really as hard as solving a generic 1024-bit factorization problem to break most VPN setups. HTTPS, or Secure Hypertext Transfer Protocol, is now widely used to encrypt connections to websites, using the TLS Transport Layer Security Protocol to allow you to communicate with a website in ciphertext by exchanging shared keys using public/private key infrastructure. So if you're logging into Facebook and you want to know that your password has been encrypted so that nobody else can see it, how do you know who you're talking to? The answer is that you look up the public key using a certificating authority, or CA. How do you know which CAs to trust? Your browser and operating system come with a list of approved ones, but this is ripe for abuse, and there have been numerous attacks. Government actors managed to get their keys in there for surveillance and interception, for example. Likewise, the CAs themselves may be attacked or issued a warrant upon by government without your knowledge. If your company is likely to be vulnerable to attack by nation states, you're better off running your own CA rather than using the standard ones. There's also the issue of what happens when authentication does throw an error. There are lots of false positives, certificates go out of date or get attached to the wrong website, for example, if one company is running the marketing campaign of another, so users end up being trained to ignore warnings presented by a browser. As in many a case, there are misaligned incentives, certificating authorities don't have any real liability over authentication, so certificates inevitably get issued negligently. A big improvement in the space, though, was brought about by Let's Encrypt, a non-profit. As of 2020, 20% of communications were still in plain text, HTTP, not HTTPS. But that was a rapid improvement even from 4 years before, where there were 60% over plain text. Even Facebook didn't enable HTTPS until 2011, so password traveled over plain text before then. But thanks to Let's Encrypt, any website can get certificates issued for free, and they also provide tools to help migrate HTTP websites and servers to HTTPS, supporting over 100 million websites on a budget of around $3 million a year. Getting people to move to HTTPS and getting more security into the browser involved a decade of nudge strategies on part of the browser vendors such as Google and Firefox to deprecate older standards through increasing warning messages. So there's another moral here. You can't make all of these changes overnight. You have to nudge people towards the secure options, otherwise they get overwhelmed by all of the false positives from systems that are set up a bit badly. So you need to give them time to change, and give the systems time to change. One of the trickier areas to lock down has always been email. SMTP, Simple Mail Transfer Protocol, is an old open standard that needs to be supported everywhere by all email clients, and by default is neither encrypted nor authenticated. If you receive an email, how do you know who it's from? The sender part of an email isn't signed in any way. If your sender is an enthusiast, then they could be using PGP to sign all of their emails with a public key, but how many of you will be checking these signatures are correct, let alone using them yourself? The problem is that these tools, hacked on top of email, are incredibly difficult to use. The famous usability study, Why Johnny Can't Encrypt, showed that the majority of users couldn't successfully make PGP work. So the real answer is that it's more likely down to subtle social cues, that people guess emails are fishy rather than pure technological mechanisms. The best you can hope for is that mail servers are set up to block the sending of emails from different domains. But with most people using the same mail servers, such as Google's or Microsoft, that isn't a particularly strong defense. With most private companies moving their infrastructure to services such as Google or Microsoft, there have been attacks here too, since email@yourcompany.com should correctly come from the same server as randomspammer@outlook.com. The other element of email security in crypto is around interception, where most services now do use start TLS to encrypt the connection between mail servers to limit bulk interception, or at least force the interception to the mail servers themselves. Still, there are issues around downgrading attacks, where a man-in-the-middle attacker can remove the request to use TLS on the message send, for which you need newer countermeasures such as MTASTS, Mail Transfer Agent Strict Transport Security, to declare capabilities around security in advance via HTTPS. And this is now starting to see support in the major email vendors at least, but it's very hard to deploy new features to such a big open ecosystem. Another aspect that we haven't really talked about yet is browser security and the security of web applications. There are big threats which remain huge to this day, cross-site scripting and SQL injection. We won't cover these in detail. This is just a pointer to them. But there are tools like the XSS Game by Google at the top, and there's also this one here, which is both cross-site scripting and SQL injection. So I'd encourage you to take a look at these so that you're aware of what these attacks look like and just how widespread they are and how easy they are to pull off if you're writing any sort of website code. Finally, if we look at the sorts of tools you'll need to know if you're interested in attack and defense on networks, it's things like Nmap here, which is a tool that you can use to scan for ports that are open and see what's happening on the network, to see whether your perimeter in your network is advertising open ports that make it vulnerable. Or whether on the flip side, if you want to attack someone who might be vulnerable, which is illegal unless you're penetration testing with permission from them, then that's what you use to find ways in. Then we've got Netcat, which is similar, but that's more about listening to specific ports to see what's happening. It's a CAT tool. It allows you to read out what's happening on the network. Then you've got Wireshark, which is a tool with a graphical user interface rather than the other two, which are command line. And this is more about packet sniffing. Wireshark gives more generic analysis, while Netcat can do things like listen to TCP and UDP protocols. Wireshark can listen to protocols from all across the stack, TCP, UDP, application layer protocols, Wi-Fi protocols, USB protocols. Wi-Fi is a tool that you can use for Wi-Fi hacking, as well as the easy ones like WEP. There are tools in here for hacking things like WPA and various other Wi-Fi protocols. Again, not only to attack people, which is bad and wrong, but also to work out whether you're attackable or your systems that you're looking after are attackable. And then there's Burp Suite, which is about attacking and defending web applications. So finding out whether APIs to web apps on the internet have vulnerabilities, you can use Burp Suite to try and find those vulnerabilities. Okay, so that's network security from threat hunting, firewalls, intrusion detection, network logging and supporting systems, the perimeter versus the deperimeter, and various kinds of attacks and defenses. So I will see you next time.